All right, so kind of our last of three major pushes on what I guess I would call dynamic memory. Again, it never really goes away, but this is kind of most of the key topics that we need to be comfortable with to build cooler stuff. So we'll go through that today, and that'll take us in the direction of our next homework. But tonight, of course, is Jigsaw do and quiz 5. So don't forget, especially about your quiz. These are getting a little tougher, a lot of syntax, I know. So give yourself time if you can. Today is a very quick lab. So although the subject material might seem a little bit daunting, it should not be challenging to get this lab knocked out, even if you got to do it, Friday morning or something. And then resurrecting a good old Lab 22 is kind of what we did in Comp 130 or Introductory C++, but we're going to be switching over to on Thursday to what we call our smart pointers. We'll talk all about what those are today. So that's another one that's not too hard to do. And then in 2 weeks, we're going to do a kind of Facebook application with a pretty comprehensive unit test, just like what we currently have for our, I guess our puzzle doesn't really have one. But in any case, we're going to be building a database, really essentially using pointers, using this new thing called smart pointers that we're going to introduce. And the reason we're learning about smart pointers is because they demonstrate how powerful C++ is when we really understand how to build copy constructors and assignment operators and all that fancy stuff we've been talking about. Once we bring all this stuff together, you can build some pretty incredible tools. And so we will get to know the smart pointer library. Really, it's in the memory library. If you want to look it up ahead of time, look up the memory library. Anyway, homework 6 will be all about that. So we're kind of beginning our journey in that direction. And quiz 6 is probably our biggest, maybe the most annoying test. I've given you 4 tries on that one because it's just kind of one where there's a lot of syntax. I apologize for that, but it's just kind of the nature of C++. So some quick review before we get in. Just a common mistake that we make if we have a .h file with a data member in it. A really painful silent error that can happen is the following. We go to develop our constructor and we're thinking, oh yeah, I need to set up this two-dimensional array thing over here. So I'll just create a two-dimensional array and create 20 new pointers. But what I just did, unfortunately, is I created a duplicate variable in my constructor that looks like this, but they are not the same thing. And so I feel really good about allocating that memory, but as soon as we leave the constructor, this goes away and I've lost this pointer and I never changed this at all. So the thing we got to remember is we just don't need to create another variable. We already have this one over here. And so we just got to just set it, right? That's really what we want to do. And we can kind of ignore, creating a brand new variable. That's going to cause a lot of problems for us, okay? And it's kind of a silent killer because it's going to just leave that memory on the table. And then when you start running your program, you're going to get crashes all over the place because you never created any memory. You just created some leaks over here, okay? So we got to hook that thing up, right? And so that's really what we're doing there when we just use that without this part right here, okay? So watch out for that one. It's real easy to do that. I've done it before as well. Essentially, we just end up masking our data member in our class, okay? Now, another one that's a little tricky when you're testing for end of file, right? As opposed to using the piece count for your for loop, you could get away with that, but there are some weird little bugs that come up when you keep checking, am I at the end of the file, end of the file? You might get an extra sort of ghost or mystery data input that can cause you some problems. So when somebody tells you that the first number in the file tells you how many pieces there are, you should trust them. That is your file format. And, if they gave you bad data, that's their fault. So use that information if it's available. And also, this is a really pretty safe way if you've got values in a file and they're separated by blank spaces. This is a really bulletproof way to load in letter, row, and column. Even if they're on separate lines, it's still going to work. But of course, in our file format, they're all on the same row, which just makes it even easier, right? So we're kind of reading this, this, and this, and then we loop and we do this, this, and this, etc. Okay, so keep that in mind. It's a nice clean way to load data in. Okay, so we get our number of pieces, and then we just start our loops, and we're off to go. Now, the other thing that I'll just point this out again. If the biggest number you run into is 37, that means you have 38 rows. Okay. If you only create 37 rows, you're going to crash. You're going to corrupt memory and crash at some point in your program. So since we start at 0 and we go to 37, that means we have 38 rows. How do I know? Well, if I'm looking for the biggest, row number, it's going to be, whatever I find plus 1. Biggest column number plus 1. So please keep that in mind. If you're having any memory issues, that will probably clean up most of the ones that I typically see out there. Okay. And then let's see. Oh yeah, here's just another way of doing this. This is just a little, a little more clever. So you can do this while I'm able to get all three of these values, right? Load from the file into there and into there and into there, keep going. And then just increment the I counter as a post increment after the I, right? So put it in position 0 and then increment, right? So this is kind of tricky, but really slick looking, right? I just don't need the for loop. I just sort of ignored the piece count altogether. But, if we got the piece count, you might as well use it. So, it's probably safer doing it the previous way, but this is a nice way to write code if someone doesn't give you the piece count, right? So just another way to think about that code there, okay? And again, watch out for that, adding 1 to that for your total number of rows, okay? And total number of columns. Uh, Last time we talked about this whole slide here. I'm not going to go over it again, but hopefully, if you got to come back and review these things, I've kind of tried to pull it all together in one place. The position of the const is typically on the left side of the integer. So if you're not sure, that's usually where we see it, or the left side of the pointer, right? Only when we want to have a const method or a const pointer do we move it to the other side, okay? So I'll let you guys go back and study that stuff or look at your Quizlets to kind of help you reinforce that. But that's most of the key rules we have to keep in mind, okay? And here again, unfortunately, there's 2 ways to have the const, before a pointer. It could be on the left side of the type or the right side of the type. It doesn't change a single thing about it, right? Left side of the type, right side of the type. It's really going to be the same thing, okay? Why they did that, I don't know, okay? But it's only relative to the star that we really care about, okay? So one last time on these 2, and then I promise I'll let it go because I know it's pretty dry. But if I have 2 variables, so this isn't an array. This is a representation of addresses in memory, address 0, address 1, etc. So I know it looks like an array. But if I have 2 numbers at 2 different address locations, and they have 2 values in them, and I decide that I'm going to have constant data, right? I'm going to have a pointer that keeps the data constant, right? So I'm hooking up that pointer, and I call it PTR read only because it's not allowed to change the data. So if I tried to, change it to a different location, that's okay, right? So I'm changing the address. These are silly little addresses, but address 4 or address 6, I'm moving it to a different pointer location, but I can't change the data that's at the pointer. That's what it means to have a constant data pointer. I can't reach in there and try to poke a value in there because it's going to tell me that's an error, okay? And most of the time, this is the animal we end up working with. It's like, hey, don't change my data, okay? Yes.
I don't know. Um, Is that how pointers usually work?
Most of the time, yeah. We say, hey, you can aim that pointer at whatever you want, but it's a read-only pointer. Yeah,
Yeah. So
yeah.
I feel like even with normal pointers, you can just say put this at address 77.
You can usually do, if there was no const here, you could do that. This would be okay. Yeah, it's like, say, put the 77 at that location. So that's okay.
Oh,
Yeah, that's okay. Yeah, and we'll do a little bit of that today back,
Alright.
but with the const there, we really can't do that. Okay.
Okay.
Now, the other flavor, again, last time I promise, when we move the const to the other side of the star, it means, hey, I cannot redirect. It's like a railroad track that I can't switch, right? I'm not allowed to change that thing to point at a different address once I've created it. It's unchangeable, okay? But I can push new data, right? So it's a slightly different meaning, okay? So how often you're going to end up using that? Hard to say. Doesn't come up that often, but it's good to know about. Okay, so into today's stuff. We're going to move on to this journey of this idea of smart pointers. Pointers are like, as many of you kind of discovered with homework 5, are kind of like, maddening because when they break in very hard to fix ways, and they can cost companies a lot of time and money trying to find those errors. So people have been trying to come up with better, safer ways to deal with pointers. So we're going to look at what does it mean to have a smart pointer and how do we build smart pointers. And so we will build our own working model of a smart pointer over the next lecture or so. But then we're going to switch over to the commercially available smart pointer library. So we'll kind of explore our own little mini version and then we'll switch on over. In the meantime, we're going to start out with mutable data members real quick, and then we will introduce this idea of rule of threes, or these sort of terrible acronyms, but if you want to impress your friends and have good interviews, you can sort of bring up these acronyms from time to time. But we'll demonstrate how they participate in the design of our smart pointers. And essentially, a smart pointer is just going to be something that wraps around a regular pointer and gives us some safety margin. Sort of like having airbags in your car, right? We still have an engine and a brake, but there are a lot of extra things there that keep us from making mistakes. So we will see how the smart pointer can actually masquerade as a regular pointer through things that we can design into its class, okay? So we're gonna create a smart pointer today. We're gonna give it a unique ID so we can track it. We're gonna overload its star operator. We're gonna delete the system copy and system assignment parts of the class. And then we're gonna also overload its arrow. And by the time we're done, it's gonna look and act like a regular pointer, believe it or not. And so that's kind of a revelation for me when I first realized I could create classes that can masquerade as other things. It's like, wow, this is pretty crazy stuff, okay? So we will do that, and I guarantee you'll start seeing C++ in a different way, because every time you look at a file, class, or any other kind of data type that somebody creates a class for, you'll realize, oh, this thing is doing a lot of really interesting things. Vectors, for example, act like an array, but they are absolutely not an array. And so we'll see that. But let's take a little side trip over to our mutable. We'll just do this real quick. It's one last thing we got to kind of sneak in here. So mutable things are a backdoor that allow us to change things when we really should not be able to change them. So it specifically relates to data members or attributes in a class, okay? So we call it a storage specifier because it specifies whether or not a particular data member can be changed when it's inside of some const scenario, okay? So you can only use data members or commutable on data members. You can't use static or const while using mutable, and you cannot use mutable on a member function. It doesn't make sense to have a function be a mutable function, right? It only really applies to data members, and it's like a backdoor thing, okay? So we'll see that what it allows us to do is just open up a little space for like having a scratch pad of information, right? When otherwise we might have a really, really hard time saving some particular aspect of what's going on in our class. Okay. So we don't want to overuse it, but we want to have an opportunity. For example, in this particular class, I have an integer here and it's got a little m as a hint that it's mutable. That's sort of a convention, not a requirement. And then we put the access qualifier over there. So that if I have a const function, notice the const is over here in this weird place. That means this function is not allowed, or this method is not allowed to change anything in the class except mutables. So mutables are that little backdoor in which it's okay to make a change, even though this particular method here is not allowed to change anything else. Okay. So we can say myfoo.mval equals 10. That's something we could do anyway. But normally we could not call a method that was making a change because it's constant, right? But in this case, we can get away with that. Okay. And then down here, if I create a constant, if this whole instance is constant, right? Normally that would be a problem if I wanted to call that method. But since I have a mutable in there, everything else is just fine. Okay. So that's really all there is to it. There's not a whole lot more. And then the question is just, where would I need that thing, right? But we'll just sort of try to put our hands to some code here real quick, sort of just adding the mutable to the class real fast, and then modifying that mutable through one of your methods, okay? So let's take a look at this real quick. I think it's probably mostly self-explanatory. Sorry about that. So let me make this a little bigger. Okay, so here we have our what we want to be our mutable. So we'll just add that to there, right? Like so. Okay. And then down below, we can kind of incorporate that into our mutable or our const method, right? So it shouldn't violate anything. Okay. And we can add a little message there that just lets us know that we actually made that change. Okay. Now inside of here, if we were to undo this one, that's going to be a compiler error for us because the compiler is going to say, well, that thing right there is not mutable. So I'm going to leave that thing commented out, but you can try it and see what happens, right? Okay, and then this one here, right? Cval is const, so we can never change that. So of course that's going to be an error. So hopefully that all makes pretty clear sense, okay? And in our constructor is of course never going to let us change a constant, so we can't do that either, okay? So let's just see if everything else here works okay, right? We're going to call our const method and it should change our mutable, okay? And we're going to call our method 2, right? Okay, see if that thing works. So that's going to continue to work, right? Right? And this will work as long as method 3 is const. So let's see if method 3 is const. Okay. So we got an error here. Passing const foo as this argument does not work. Let's take a look at what's going on here. So method 3, just while we're here, let's go look and see what method 3 is trying to do. Method 3 is a non-const method. Okay. And we're calling it from a constant instance, okay? So this often catches me off guard. It's like, wait, I'm not really even doing anything in method 3, right? So see, method 3 here is just doing nothing. But still the compiler is saying, well, this thing isn't a constant method, so you are not allowed to call it from a constant instance, okay? So notice that, sorry, cfoo is a constant instance, okay? So these are the games that we play when we start messing with consts. It sort of invades all of our code. Things that are not violating const stuff we can call, but the compiler can't tell that method 3 isn't violating anything, okay? So we could add a const to that method and that should make that thing work, okay? So I know you guys probably thought we were kind of done with const, but that's kind of as far as we're going to go with that stuff, right? So I'll just make that compatible with the const, and now we should be okay, right? So everything kind of works, okay? So just kind of showing you how these things interact. The key takeaway here, though, is that M, or mutable values, can be changed in all sorts of situations where we might not otherwise be able to do that, okay? So kind of leave that for you to consider. There's a lot of code here. I know it's a bit hard to see on the screen, but this is all of the stuff we're kind of considering here, okay? So let me leave you guys with that, and just show you two more slides and see if I can pull this together for you. So if I had a constant instance of a class over here, right, something that I had declared to be const foo, and I tried to call a method, that would work as long as that method was trying to modify some mutable data member. Okay, so that kind of allows me to call a method, a non-const method, with a const instance. Of course, we could directly change it too. Or we could call a constant method that also changes that mutable data member. So that's kind of like what we were seeing here just a moment ago. If I have a normal instance, I can call and change normal data members, non-const data members, right? And of course, I can still directly change a mutable data member at any time in a normal instance. But if I try to call a const method, the only thing I'm going to be able to do is modify a mutable data member there, okay? So don't worry about memorizing these things. The high level takeaway is usually you're going to be surprised by your limitations once you start introducing these const things. It just takes a little bit of practice to get used to, what the impacts are going to be. Okay. Okay, so let's sort of leave that behind for the most part now. We'll come back to it when we find some good applications for it. But let's talk about this concept called RAII, Resource Allocation is Initialization. It's a terrible acronym, but it is nonetheless one that is understood and talked about in design for code in all sorts of languages. So what it means is basically when you create an instance of something, your constructor kind of creates a lot of memory, kind of like in your puzzle constructor, right? Or for your puzzle, and your destructor cleans up the mess. So resource allocation is where we initialize all of our stuff and then we throw it away. It's a really simple idea and one we're going to see from now on in the class. Some people refer to it as scope bound resource management because when you go out of scope beyond the curly braces, the destructor gets called and cleans stuff up. Okay. So these two pretty much mean the same thing. And it really means we just have to be careful about cleaning things up in our destructor, okay? Whenever we create something in our constructor. As we will see today, we also might be able to restrict or might need to restrict what happens when you call the copy constructor and the assignment operator. Sometimes we don't want those things to be active and we want to take them out of our class. So we will be doing that today. And whether you realize it or not, string and vector and array and all of those other containers that we studied and used utilize the same techniques we're going to look at today. So if we could crack open the code for the vector, we'd see a lot of the stuff that we're going to cover today is implemented inside of those classes. And when we get to our lecture on Thursday, our shared and unique pointers from the memory library are actually going to use those same ideas. Okay. Um, so let's kind of dig in and we're going to build our own class that tries to masquerade as a pointer, believe it or not. So we're going to call this smarter pointers. It's not the smartest pointer, but it's going to be smarter than the stuff that, we currently work with at a very low level. But let's look at the problem we're trying to solve here, okay? So we want to make a pointer clean up after itself after we're done using the pointer. That is, if we're done with a pointer, maybe it should delete the memory that it was pointing to. So here's the problem we have. I have a pointer over here on the stack, and then I have this heap instance of a class, and I'm holding on to that pointer kind of like that, right? So when f pointer goes out of scope, we get rid of the f pointer, but by default, this little thing over here ends up just floating around. So we want to find a way to make this thing go away intelligently. So we want to have it kind of like this: smart pointer class, create an instance of something, right? As if it's a pointer, but notice we didn't put a star there. We're just saying create this P0 thing, an instance of that class, and then hook it up to some new thing on the heap. P0 equals give me a pointer, right? How's that going to work? We don't know yet, but we're going to see that in a second. Or maybe I want to create a new P1 pointer based on something I passed directly through the constructor. So these two are pretty much the same things here, right? Here we do it in 2 lines. Here we do it in 1 line, right? Or maybe I want to do another pointer over here. And then maybe I want to say, hey, follow that P1 pointer and get me whatever the value is and print that out, right? So it should be an integer of 1, right? So we should get a 1 over there. So this is the system that we want to build, okay? And I also would like to say, hey, if I set P1 equals to P2, what should happen, right? So let's just look at this for a second. If I want to set this pointer equal to what P2 is pointing to, we would like it to redirect and get rid of this piece of memory. We want it to automatically delete that other thing over there, because otherwise that would be a memory leak. So there's all sorts of intelligence that we want to put into our assignment operator, kind of like you guys were doing with your tri-matrix labs, okay? So there's a lot of potential here, but we're going to need to overload the assignment and the copy operators in special ways to do things the way we want them, right? And so ideally, when we go out of scope, all of this cleans itself up automatically. No dangling pointers, no leaked allocations on the heap. Everything should just be scope bound, right? When it goes out of scope, it cleans itself up automatically, so that the destructor for the smart pointer cleans up the memory that it was holding on to, if it was still holding on to any memory. That's our goal, right? We want to have these features in our class in some way, okay? So, and it'll be easier than maybe you think to actually do that. So let's start our pointer class here. So we're going to have simply a pointer to an integer as a data member in our class, okay? And then we're going to say our default constructor is going to initialize that pointer to null, all right? So what we're saying there is, hey, if you don't give me something in my constructor, I'm going to set my data member to null, okay? But if you give me the pointer to an integer, I will set my pointer equal to that integer pointer, okay? And when I go out of scope, I'm going to delete what I'm pointing to, assuming it's not null, right? So there's a little bit more code that's needed there. So this is where the magic starts to happen. It's like, oh, when you go out of scope, you're going to trigger your destructor. And if this is pointing to some memory over here, please do that cleanup for me automatically, okay? So that's where we're going to start with our smart pointer there, okay? And it's really, again, it's just holding on to a pointer, and it's got some policy that it's going to enforce to keep us out of trouble. And we'll add more stuff to this as we get fancier, okay? So there's our kind of basic class. We should be able to do this, right? And then we should also be able to do this, right? So now we've got our new allocation on the heap, right? We did the new right here, and we passed in the pointer, right? So this is what created the new integer, and it just passed the pointer into the constructor, okay? So this happened and then passed its pointer into the constructor, and we just copied it over into the private data member over here. okay? So that's us constructing some different pointers, right? Pointers to integers on the heap, okay? So our class is kind of starting to look a little bit like what we want, okay? So let's take a look at what happens when we go out of scope. So here's our class again, just for reference, right? So if I create a pointer that points to nothing, it's going to trigger the constructor and then immediately trigger the destructor, because that's just how those things work, right? We said when this goes out of scope over here, we destruct, okay? So it doesn't do anything for us, but it's going to automatically, take care of anything that was potentially created, okay? So now here's something a little more useful. I create a pointer and I say, hey, we're going to manage a pointer to this 2 over here. But then eventually somewhere down the line, I go out of scope and now it triggers the destructor and I'm going to delete what that thing points to, assuming it's not null, right? So now that goes away and the instance goes away. And that's a really good situation. We didn't even have to delete anything over here. The destructor did it for us. Okay, same thing over here. We got a scope and then SP3 triggers the destructor, which gets rid of the integer and everybody's happy. Okay, so we're sort of starting to head toward our ideal situation here. But as we're going to find, without having some extra diagnostics, it's going to get pretty tricky here real quick. So we want to add an ID, a private data member ID, or public for now, just so we can tell who's deleting what, because it will get kind of confusing here, okay? So what pointer is really getting deleted by the destructor? So giving our class a kind of, little ID is going to help us, debug that, okay? So there's our ID. So now we've kind of grown our data members a little bit by adding an ID. And we want our constructor, we're going to just take a really cheap way of doing this. We're going to pick a random number between 1 and 1,000. And this is really not the way you do it in the real world, but it works for class. So we just say rand modulo 1,000 plus 1, and that'll give us that range. And so out in the real world, we would never do this. We would find a better way. But let's just do it here in class. So here's our add an ID. There's our pointer. Here's our constructor. Notice that I've set the default value for P to be null pointer, okay? So inside of our constructor, we'll assign a random number, and then we'll print that information, and then we will copy whatever P is into our data member over here, okay? So that's our basic constructor. And this really should have an if, right? If PTR is not equal to null, then delete, because otherwise we might actually creating a crash there, right? So a little bit of logic there is probably a good idea, okay? So in main, we now should at least be able to create what we saw on the screen. And notice here, when I create a local scope for no reason whatsoever than to just try it, we should see the destructor trigger right here for SP3, okay? And then down here, we should see the destructor for SP1 and 2. Okay, so this is just a way of verifying that the destructors are behaving the way we think they are. When something goes out of scope, we should see that destructor get triggered. So let's see if we can put this one together. It's not too much work, really. And then we'll start adding some more cool stuff to this thing pretty quick. So let me get to here. So let's go into our ID. So we'll say int ID equals, or we'll just leave that as nothing for now, okay? And then inside of our constructor, we'll say ID equals rand modulo 1,000 plus 1, okay? Plus 1. And you can make it 1,000,000 if you like and improve your chances that you'll never have a problem, okay? But then we steal that pointer, put it over there, okay? And down here, do we want to add a message? Oh yeah, cout created smart pointer with ID equals, and we'll put an ID in there, right? This is our ID, just so we can keep track of what's going on, okay? And then I'm gonna make this a little safer code, I'm going to say if PTR is not equal to null pointer, PTR, then go ahead and delete what it points to, right? What is pointed to by PTR, okay? Delete that thing, okay? And everything down in main should just work for us. And we should see SP3 destruct first before SP1 and 2, okay? Let me see if I got that right, okay? So I created a smart pointer with an ID randomly assigned 387. It was a null, right? And then I created a 887. And there's the actual raw address of what we're pointing to, right? Being managed by our new smart pointer, right? Okay, and then we destroy, I forgot to update my destructor here. Sorry, let's do that real quick because I do think that is helpful. So where is my destructor? Destroyed with ID equal ID. Okay, ID. And now we can kind of see that the third one that gets created is 778, but that's the first one that gets destructed. So that's our SP3 going out of scope. Okay. And then we have SP1 and SP2. Okay. So everything kind of is working as we would like, right? We should feel some comfort that the rules of coding are applying in this situation. Okay. So there's my constructor, there's my destructor, okay, and there's my main over there. Now, we haven't really made these things behave like pointers yet. So you're probably still kind of not really clear where I'm going with this idea here. And just a couple high points here. I think probably I covered these. Right. So this smart pointer so far only works with integers, right? So if we go back and we look at our solution, it's like, well, yeah, we've kind of created a smart pointer, but it's only really working for integer pointers. Well, that's trivial to fix with a template. So remember that we can templatize a class. And now instead of that being int, it could be double, it could be float, it could be foo, it could be token, it could be puzzle piece. So really, we don't even really need to worry about what kind of pointer we're really dealing with there as long as we templatize that thing. Okay, so that's a really nice thing to look forward to. But let's add the ability to dereference through overloading so we can get the integer back out from our pointer. So here's us creating that pointer again, right? I want to be able to say what P points to is star PTR, right? But here PTR is an instance of a class, but we're treating it like it's a pointer. If you remember our pointer basics, it's like, okay, star PTR is going to give me what it points to. So we can add that little trick to the class so that it will act like an actual pointer, even though it is clearly an instance of a class, okay? So, and that comes from overloading the star operator. And remember that the name of the method is operator star, and then we give it a pair of parentheses, and we say what it's going to give us back. It's going to give us back a reference to an integer. What integer? The integer that's pointed to by our raw private pointer on the inside, okay? So this is our first really good trick that we're teaching our class here, okay? It knows what that star means. So now I can do that. I can say, hey, there's a smart pointer managing a 5. Print me what's at the smart pointer. And it should just return that address, or it'll dereference the raw pointer and return that integer as a result of the function, okay? Which is pretty darn cool. And now we're starting to seem like we're dealing with real pointers here. So I can say cout, sorry, there's a little typo there, cout less than what's at SP plus what's at SP. So I can do math with it right in line, right? It just works that way, which is really slick, okay? I can even just right now do that. I can say, hey, go put 10 at the address where SP is managing, and it will overwrite that 5 with a 10. And that just works right out of the box, which is pretty darn cool. So we kind of are halfway there to creating a smarter pointer, okay? So there's our dereference. We're just overloading the behavior of the star operator, okay? So let's look at kind of a couple scenarios here. So C out star PTR2, that's what we're printing, right? We're following the raw pointer and getting back the 2, or we're following the raw pointer off of the SP3 and getting back the 3 there, okay? Now, if I were to try to dereference this, that's a little bit of a tricky question. Like what do we return from that function if the PTR is null, right? We don't want to dereference null and crash. So we might need to raise an exception, for those of you who remember exceptions, or just return a 0, but that's probably not correct either, right? So there's some questions on what do we do if someone says dereference a pointer. As we all know, if I try to dereference a bad pointer, my code is going to crash. But at least we may have an opportunity in our class to raise an exception or do something that at least tells me via message, hey, I'm going to crash now because you tried to print a null pointer. It's like, oh, now I know where to go fix the bug, right? So we just got to kind of, think about how we want to handle that. Okay. But we've added quite a bit, right? So so let's see if we can do this real quick. Okay. And here's that question. How do we dereference a null pointer? Okay. But let's take a look at the code here. And also the return value, you noticed, of our overload has an ampersand. So we'll look at what the impact is of actually removing that. Okay. So let's take a look at the code. Okay. So we're going to go down to our class. Here's our constructor. There's our destructor. Okay, let's write the overload. So we're going to say we're returning an int ampersand operator. Whoops, my keyboard fingers, right? Operator star. That's the name of the method. That's the parentheses for the method. It's got no arguments, right? And then we will kind of just set up our curly braces and just say return dereference PTR, okay? And we probably should say if PTR is not equal to null PTR, then return what it points to. Else, return 0 just makes the compiler happy, but it's not really a great idea. But we'll just start there, right? See where we go, okay? And then down here, I think we've got everything written already. It's oh, here we go. So here we're going to create SP3. Let's print out what it points to, right? C out star SP3, okay? ENDL, okay? Okay, and then you can do these other ones if you want. So I'll just leave those off for now, okay? Let's just see if we kind of get there. Oops, else return 0, non-const L value reference. So I can't return 0 if I'm trying to use a reference, right? So where did it go? So this is not compatible with that, right? Because I can't return a reference to a literal. So let me just take off that ampersand for the moment, right? And so now we have our SP1 pointer, SP2, and the printout for our 3 there. We can actually finally see what we're having off of our SP3 pointer, right? It's got a 3 value. Questions, anybody? Make sure everybody's got a chance to absorb that. So not a great solution over here, right? We kind of need to have a better solution, and different classes deal with this differently. Some classes will return an instance of some special non-value class, right? Or some will just raise an exception and your program will crash unless you catch the exception, which is probably not much better than regular pointers. So certainly a better solution is sort of called for here, okay? But at least we've got kind of our star thing kind of added there, right? So we can minimally, we can print a warning and just say, hey, I'm going to crash now, right? Otherwise, I'll go ahead and just print out what's at that pointer. Okay. So one of the reasons we put the ampersand on there, right, and it's good to have it, is so we can use this thing in sort of an expression, right? You return something and that gets used in another expression as part of a larger equation. So for example, let me go back to our code. If I wanted to do something like this down here, this will be the last one and I'll move on. So if I wanted to say cout, if I want to say sp3, what's at sp3 equals the sum of what is at sp2 plus what's at sp1, okay? This code will not work without having an ampersand there, okay? So we won't get the proper result and be able to use that in a larger equation in order to assign it here. So we're going to have that ampersand back for that thing to work, okay? So normally that's why those ampersands are there, and we'll just sort of say else, print error message, right? Cout error, okay, quote, ENDL, and we'll return something anyway, right? Return star PTR, and we'll still crash, but at least we'll get our error message, right? Okay, so a bit of a sloppy solution, but okay. So there's our error and our crash, right? If we try to do something that's already known, okay. So anyway, that is kind of the next step for us, right? Haven't got a great solution to our null pointer, but we've added this new capability to our class, okay, which gives us some nice things. So the next thing we obviously need to do is add the error or the arrow. But first, let's look at the reality of making basic copies and assignments using the copy constructor and the assignment overload that are built into C++. So remember we said, if I take something like SP3, right, and I assign it, overwrite it with SP2. So let's look at what's going to happen here. If I say I have something with ID 26 and 39, and I'm going to say SP3 equals SP2, by default, without us writing a assignment operator, right, for the equal sign, C++ has its default one, and it's just going to copy the ID over and the pointer. So now SP3 and SP2 are pointing to the same integer, and we have a memory leak, okay? So that's not really great behavior. It works by default, but that particular assignment operator that is built in isn't really very nice, right? It leaves us with some leaky data, and maybe we didn't really want to actually do it that way, right? And now when SP3 goes out of scope, guess what happens? Our nice little class tried to be helpful and deleted the integer 2 and has now undermined SP2. So now SP2 is pointing to something that's been deleted, and SP3 has leaked memory. So this kind of automatic thing that we get for free here is kind of causing us some problems, okay? So this is not how we want our pointers to work, okay? So we have some design questions about what we want to do. Do we want to let that happen at all, right? Do we want to support that kind of assignment, or do we want to get rid of it, okay? So this is our shallow assignment, and it's not a great idea, okay? Because we're going to probably crash here, okay? So similarly, when we copy something, so notice here, I'm constructing something based on a copy, right? So I'm saying, hey, I want to construct SP3. Same problem, we're just experiencing it in a slightly different way. So we're still constructing something that's a duplicate, and we're leaking, and we're also undermining the other pointer there, SP2, when SP3 goes out of scope. So neither one of these things in their default behavior is very good for us. So we're going to need to change it, okay? So we kind of don't want the leaking. We don't want to undermine memory. So we could decide that we want to keep track of how many pointers are pointing to something on the heap. And that is what the shared or smart pointer type does from the memory library. So we're not going to try to write the code to do that because that's just way more code than we want to write. But there is a system that we're going to use. We're called shared pointers, where they have a very elaborate way of keeping track of how many people are using a particular chunk of memory. And for those of you who've worked with Python or JavaScript or even Java, and have heard about garbage collectors, we're sort of kind of seeing the beginnings of a garbage collector. A smart pointer, and we'll see this in the memory library on Thursday, but a smart pointer that knows how to keep track of who all is using a particular chunk of memory. Now, for our project today, we are not going to try to do that. We are just going to delete entirely the assignment operator and the copy constructor from our class to prevent that from being legal at all, okay? So we said by default, we get these things in there and we don't want them. So if we want to delete them from our class, and this is a little bit strange, I know, we have to say, hey, my copy constructor is getting deleted. That has to go in my class. So we're literally telling C++, don't do your usual free thing of copying stuff, right? So that becomes illegal. And similarly, I say, get rid of the assignment overload that comes with the system. Delete that thing. And that will make that thing illegal, okay? So at compile time, these will raise an error if you try to do them. And we'll remember, oh yeah, I'm not allowed to do that with this kind of sort of smart class that we built, okay? So when we get to our memory library, we'll see that that is what we call a unique pointer. It can only ever manage one piece of memory at a time, okay? So that's the strategy we're going to follow here. We're going to delete those things from our class here in just a second. And we're going to essentially treat that as an illegal piece of code when working with our class. So let's delete those things. So again, all we got to do is just add this one line of code to our class, right? And then add this other line of code to our class. And the compiler will then catch anybody trying to actually use those basic operations in main, okay? So let's actually go look at that code. So I'm going to try to get that thing out of there. I can never remember all of it exactly, but so here's our method for the star, right? Copy constructor down here. We want to delete that thing. So let's just go look again what that is. Smart pointer, const smart pointer, ampersand, some variable. So we're going to say smart ptr const. All right, yeah. Smart pointer const smart pointer tr ampersand right hand side, right? So whatever somebody gives me on the right hand side of the equals, if that happens, don't do anything, right? So the compiler will see that's there. It'll be like, oh, that's an illegal operation. You can't do that, okay? So that's this one here. So now we're going to do this one, smart ampersand operator equals. So let's try that. I'm going to steal this here so that I can go a little faster. So I'm going to say smart ampersand operator equals. That's our assignment overload. Whoops. Oh, I'm in insert mode. Operator equals const smart ampersand right hand side equals delete. Okay, so that's deleting our system level assignment operator, right? Okay, I think we got that right. So now, if I run my code, I'm probably going to get a crash. So look, it says operator equal declared as function returning function. Okay, smart ampersand, and it says, yeah, it's been deleted. Okay, so that is the compiler telling us I cannot. I think I have a little bug on line 66 though. Let's look at 66 real quick. Did I do wrong on 66? Oh yeah. Now this is saying, hey, you can't do that anymore. So that is no longer supported by our class. No copying when constructing, right? And then the other one is, this is no longer supported by our class. No assigning things between copies of our instance, okay? And I still have a little error over here. Operator equals, somebody's, oh, I left out my, did I leave out my, What did I do wrong there? Const smart ampersand. Sorry, if somebody sees it, give me a shout out there. Const smart ampersand right hand side equals delete. Oh. Ampersand. That it? No, still. I'm staring right at it. Smart pointer, const ampersand. Oh, smart, not that. Sorry. Oh, thank you. Oh, gosh. Yeah, thank you. I appreciate that. Yeah, I wasn't seeing it. Right. Okay. And so now down here below, after smart say, okay, was not declared. Okay. So then we just have SP3 is something that's not been declared because we didn't create that thing, right? We had to take out the SP3. Okay. So I think anything related to SP3 we take out and we should compile. Okay. So a little messy, but nonetheless, what we're trying to do is raise the error at compile time so no memory corruption happens. So by adding these kinds of things to the class, we're making a really strong policy decision that we won't support those kind of operations. Okay. So we're sort of intentionally removing this capability from our class to save us from accidentally creating memory corruptions later on. Okay. Now we could go ahead and write those like you guys did for the triangle matrix, right? So we took a shortcut today, but we could go back and write some really elaborate stuff there, but we're not going to really do that as part of our exercise today. What we want to do is go on and just finish a little bit more of our class before we kind of wrap up and implement the overload for the arrow, right? So the arrow operator allows us to reach into the class and pull out something, right? Even though, we're not dereferencing, it might be that we're pointing to, let's say, a token instance, right? So notice I've changed my data type here, not to an integer, but to an entire instance of a class. So now I'm going to be implementing not only the star dereference, but also the arrow. So I can say, hey, SP1 arrow letter or SP1 arrow row. Okay. So now I can do this. I can say, hey, create an instance of a token, pass the pointer into the constructor, and then I can say SP arrow letter. So here again, what we want is SP to act like a pointer, even though it's an instance of a class, and then we overload the arrow to get at the letter, okay? So now we're really starting to see this thing as a pointer, okay? So here's our token, very similar to what you guys are working with in homework 5, right? So not anything really different there, just instead of an integer, it's got a little more substructure to it, okay? So let's see if we can add this thing. Okay, so, oh, I knew I was going to do that. Let me reshare, sorry. Start over again on our arrow down here. Did the dereference, deleted the system copy. Okay, so we're all the way on our last exercise here. So bear with me here. We'll get you guys wrapped up a little on the early side. So again, we want to add that arrow overload. So let's go down there and do that thing real quick. Okay. So we've got our convert integer to token, right? So we're going to make this a token pointer. Okay. Oops. Right. And our token class should be there. So our constructor is expecting a token pointer as well, right? And I promise we'll come back and templatize this. And then we have our destructor. We're going to say, okay, I would like to have I want to return a token, right? Ampersand, right? So that's our overload for the star, okay, with our warning and everything in there. And then we will say, if you use the arrow, return the token star, right? So, or actually what we're returning there is actually, yeah, token pointer, right? Okay. So again, we're just returning the raw pointer in this case, right? So that we can simulate the arrow. This one may be a little bit surprising, okay? And I think I might need the ampersand there. Yeah, let me see if I can put that token ampersand in there. A little bit unsure about that, okay? Okay, so there's our copy, deleted copy constructor and assignment operator. So now what are we passing in? We're passing in a pointer to a token, and I think we got to give it like a row 2, column 3, okay? So this constructs a new token and the pointer gets passed into our smart pointer, okay? And now if all this is working correctly, I should just be able to say SP1 arrow reached in following the pointer that I returned and print out what that row value is. So got a little bit of a, I think I got to get rid of that ampersand. I think that ampersand was being a little ambitious there. I think I just want the pointer. There we go. Okay. So SP1 row is 2, right? So that's this part down here. SP1 row. Okay. So the whole idea, again, just sort of summarizing, is to sort of make these classes look more and more like something they're actually not. Have them sort of take over what seems like a pointer behavior. And if you think about our iterators for our list container for homework 4, Blackjack, those iterators are exactly that. An iterator is a class that is acting like a pointer by overloading the star and the arrow operators. So even iterators are kind of like smart pointers a little bit, okay? So, and you can go on and implement all this stuff, right? But we're not gonna try to add too many features because this thing already has been invented. It already exists in this memory library that we're gonna actually see, okay? So, but the good news is once you learn how to use dots and arrows, we can steal that pattern and use it in lots of other places. We don't have to relearn that stuff. So next time when we come back, we're going to look at the memory library, and what we built today comes really close to what's called a unique pointer. And we'll look at that next time. And if we have time, we'll also look at the shared pointer, which is a really cool system that a lot of people have started using because it's very clever. It's a little bit like a little mini garbage collector for pointers, okay? And then we'll study the weak pointer as well. This will come in handy for our Facebook homework assignment, okay? So weak pointers will actually be helpful for homework 6, okay? Terrible spelling there, okay? So for our lab today, all we're gonna do is try to tokenize, or templatize the smart pointer class that we wrote. So what we'd like to be able to do is smart pointer double. Oh, right. So notice here, we're sort of just creating, this is what we did today with our double pointer type, but we want to be able to do this smart pointer, give it a token as its type for the pointer, and then create a new token. So let's pause here for a moment and make sure that we all get that, right? So we're going to call our class, and once you tokenize it in main, you can give any data type you want as the template. Starting to look a little bit like a vector, right? So when we say vector, we say a data type, and then we say the variable name of the vector. Well, here for our smart pointers, we're going to say smart pointer, I want to point to a token, or I want to point to an integer, or I want to point to a double. Then we'll create the instance of the class, and then we'll feed it the appropriate kind of pointer. In this case, if I choose token, I have to feed it a token pointer by calling the token constructor with the new symbol, right? And that kind of ties us all together. And that's a pretty cool little class, right? It can do a whole lot. We can manage pointers of any data type that we want to feed it through that token for that template, okay? We can even come back later and say the SP arrow and all that other stuff we just added. Okay? So in the code, let's just take a look real quick, and then I'll let you guys kind of do what you got to do. But we've got our token class. Now, for those of you using Replit, this token class will be in a token.h, right, and a token.cpp. But for folks who are just on Program IZ, I didn't use Pro this time. I just did the online compiler. So our token is broken up in the main.cpp file. This is like the equivalent of token.h, and this is the equivalent of token.cpp, okay? So, and these are the token.cpp items there, right? So down below, here's our smart pointer. You need to templatize the class. So you'll have to remember how you do that and then introduce anywhere you see the double, that's going to be our template type, right? And it's only there in 2 different places, thankfully, okay? And surprisingly, the rest of the stuff should be pretty easy. This looks like a little whoops, wraparound problem here. So I think you guys can sort of figure that stuff out. But let me leave you with that. And if you got to work on your homework, all good. Otherwise, we'll see you on Thursday and we'll talk about this new memory library thing. Okay. Thanks, everybody.